Hi everyone, this is Jessie speaking. Welcome to our KDD tutorial, Learning with More Data. So this is a joint work between Penn State, University of Minnesota, and Shanghai Jiaotong University. So I will go ahead and get started, and then the rest of the part will be shared by the other speakers. I'll start with the motivation. Everybody says we live in the big data era these days, and a very representative dataset is ImageNet, which has more than 14 million labeled images. So everybody knows this dataset. However, when we are dealing with our real tasks, maybe we are facing the challenge of the small data that we only have a small amount of data. Take image classification for example. Say, even though we have more than 14 million images on ImageNet, maybe the task we care about is to classify these two types of dog, which they look very much alike, Boston Terrier and French Bulldog. I bet for the audience who never saw any of this kind of dogs before, maybe it's very hard to tell the image I show here whether it's a Boston Terrier or French Bulldog, because I'm only showing you 6 labeled images. And that is actually a Boston Terrier with the question mark over there. So this is an example of few data samples which make the learning task very difficult. Another example is when we are training robot to do stuff like human, we may want to only show the robots a few samples. Say, for example, place this ball in the from the bowl to the plate, and whether the robot can actually learn from that very few data samples of behavior, so the robot can repeat. That's another small data example. And something that also relate to my research is we do a lot of research on mining spatial temporal data, in particularly city data. And we find nowadays many big cities have started open city initiatives where they put city data publicly online. For example, New York City put a lot of data online. They have a New York City open data portal. If you search for, say, taxi data, New York has a very good taxi data set, and they keep updating it. So does Chicago. You can see a lot of taxi trip data that is public online. Uh, However, when you search for taxi data on Boston website, you don't find any such kind of data set. So this is another example that if you want to predict the taxi demand in Boston, and that's going to be very difficult because you don't have a lot of historical data set. So what if you only have small training data and you still want to use such data for your machine learning tasks? And typically, there are two ways to get help. On one side, you can get help from auxiliary tasks, which are the tasks that may be similar to your target tasks. And you can also get help from domain knowledge. So our tutorial will mostly focus on these two categories. On one side is how to transfer knowledge from auxiliary tasks. And another big category is how to use domain knowledge to boost the performance of machine learning model when we face small data. I'll get started with the first category, how to transfer knowledge from auxiliary tasks. And so just give an overview. The idea of this big category is that we have some source tasks, and from those source tasks, we can train a model. And then we transfer the knowledge. Basically, we transfer what we learned from the source task data to the target tasks. and we train a new model for these target tasks. And here we present three types of learning techniques for this, how to make use of the auxiliary tasks. First is the transfer learning. In the transfer learning, the setting is that we only have one source task, and we also only have one target task. And for the multitask learning, we have n source tasks, and we have the same n target tasks. And for the meta learning, the setting is we have n source tasks, and we have another n plus 1 target tasks. So they actually deal with different kind of settings. So we will talk about representative technique for each of the category. We'll start with the transfer learning. So for transfer learning, as we just said, there's only one task and another target task. And so a big category under transfer learning are supervised transfer learning and unsupervised transfer learning. So the difference between them is whether the target domain has a few label data or has no label data at all. And usually in the transfer learning, we assume the source domain has enough or sufficient label data to learn a reliable model. But for target domain, we don't have too much. So we'll talk about the first one is how to do supervised transfer learning. And this category maybe most people are quite familiar with. So in the supervised transfer learning, so let's say we have the same task, and this task is to classify whether this image is a Boston Terrier dog or a French Bulldog. And since we only have 6 labeled images, that's definitely not enough for us to learn a reliable model to differentiate these two kinds of dog. So typically nowadays, the state of art is actually we'll use the ImageNet, in particular for image classification. We'll use the ImageNet to learn a source model, and we use this source model as our base model, and then further fine-tune based on the images we have for our target task. So typically people use neural nets or deep learning. So the idea is for the source task, this is the neural nets we learned with multiple layers. And for the target task, we make the lower layers share the same kind of we make those layers share the same kind of parameter. We call those tied layers. And then the upper layers we call adaptation layers, and those layers are trained or say fine-tuned on this target label data. And the reason we are doing this is usually the lower layers will capture the fundamental semantic understanding of the images. For example, if we're doing face recognition, the lower layers probably will detect some of the meaningful sub-images that tell this is a human's eye or nose or eyebrow, those kind of stuff. And then the higher layer are more towards classifying certain kind of people's face. So the similar idea is here. So the lower layers may capture the dog's nose, eyes, and ears, etc. So another type is unsupervised transfer learning, where the target domain has no label data at all. And the idea, since the target domain, we don't have any label data. So the idea is actually we try to make the target data, the feature space, has a mapping that's similar to the source data feature space. And in the implementation, we usually add a term that's the loss on the distance between between the source data samples and the target data samples in the feature space. So to give an example, mostly frequently used distance is the MMD. So is the maximum mean discrepancy. As you can see here, say this is a source domain, and this is the target domain, and this is the two-dimensional feature space. So we are learn a mapping that map them to this new feature space. And in this feature space, we hope that the distance between the source and the target data are small. So basically, we try to minimize their distance. And the way to define this MMD, as you can see in this formula, so XS are the data samples in the source domain and XT are the data samples in the target domain. If you define them as MMD, and that's defined as basically you take all the data samples in the source domain and take the mean of those data samples. And you can think about this is like a representative data samples of all the data samples in the source domain. And similarly, you take the means of all the data samples in the target domain, and this, of course, this is after the mapping. Okay, after the mapping, you take the mean of those data samples, and then you want. So basically, you see the difference between the representative mean data samples in the mapped space between the source data and the target data, and you take the L2 norm of that. So you try to make in the new mapped space the source data and the target data to look similar. This is most frequently used measure, MMD, and in particular is used in this ICML paper. So basically, as we just said, so we have some tide layers shield the lower layers, and in the adaptation layer, so we try to make the source and the target to be similar in the feature space, in the mapped feature space, by measuring the MMD distance between them. And a more recent work, that's ICCV 2019 paper, they changed the MMD to a new distance measure. They call it MMFND, and this is the basic maximal mean feature norm discrepancy. And you can see they look very similar, okay? But the difference is, so first they will take the L2 norm of the mapped data. So F and G basically are the mapping of the data. So G are the lower layers, and then F are the tight layers. So basically, you map those data first, and then you take the L2 norm of that data. And then after that, you sum, or first sum over all the norm of all the mapped data samples in the source domain, and you take mean over that. And the minus, well, you sum over all the norms of the mapped target data samples and take the mean of that. So basically, you first calculate the norm first and then see the difference. So that's different from the previous one where you calculate the distance first and then take the norm. But this method surprisingly works very well. And for more details, you can look at this paper shown here. Of course, another way to make the data in the target domain and the source domain to be similar is using the idea of adversarial method. So basically, you have a mapping and you have a discriminator, and this discriminator try to differentiate whether a data sample is from the source domain or the target domain. So you basically want the source domain and the target domain to be similar after the mapping. Okay, so that's the big idea of this unsupervised transfer learning. You're basically mapping the data samples from the source domain, target domain to be similar. And that's all about transfer learning. So we move on to the multitask learning. As you can see from this figure again, so the multitask learning, different from transfer learning, usually has n tasks, and the target has the same n tasks. Okay, and in terms of method, there are three type of method called hard parameter sharing, soft parameter sharing, and task routing. So actually, the method is quite straightforward. Let's say you have three tasks, task A, B, and C. And the hard parameter sharing is basically make the lower layers to share the same kind of layers in the neural nets. And the soft parameter sharing is to allow the difference between those bottom layers, but having certain constraint to make them look similar. Okay. Uh, so those are two very straightforward methods, and more recently, there is a method that's kind of taking the advantage to make it more soft. So the idea of this method is called layer routing. Uh, so this idea is actually some of the layers they are shared as colored in orange, and some of the layers are probably task specific, like the pink for this task and the yellow for this task. Okay, and maybe some of the layers are even skipped. Okay, so different from the hard sharing or soft sharing. So this framework is more flexible. And in terms of the implementation, the loss function has three terms, and this is our typical term of the loss function to be similar with the labels. And this is a sparsity, basically to add all the weight together to make the weight to be sparse. So most interesting is the last term in the loss function is the sharing. So basically we want the weight. So basically we want encourage them to share the same layers, especially for the lower layers. We would encourage them to share the weight more. As you can see, the lower the layer is, the smaller the lowercase l will be, and the weight will be larger. And then we want the weight on those layers to be similar. And this is straightforward because usually in the neural nets, the lower layers are the fundamental building blocks of the images, and the higher the layer is, the more task specific it is, and we allow them to be more, specific towards the target tasks. So that was the idea of this paper, and that is about the multitask learning. So for the next part for meta-learning, Huaxiu will take over and talk about it.
From Penn State University. Thanks, JC, for introduction. Here, I'd like to introduce some recent research about meta-learning. I will introduce meta-learning from two parts. The first one is about two types of meta-learning algorithms, the gradient-based meta-learning and the metric-based meta-learning. And then I will introduce two challenges of meta-learning, the task heterogeneity and the meta-overfitting. Let's start. And in the meta-learning, that our goal is want to learn and summarize the skills from the meta-training tasks. And it seems like we learn a lot of new skills from the meta-training tasks, and we know how to learn a new skill. Then we reuse this learned knowledge and transfer this knowledge to facilitate the learning process of the new task. And in the new task, we only need maybe a few trials in the reinforcement learning and a few samples in the supervised learning. So to facilitate the learning process of this new task. Thus, the meta-learning is equal to learning to learn. So we learn from the tasks and we know how to learn. Here an example of meta-learning for the few-shot image classification. Let's see that in the meta-training part, we have a lot of training data set. The training data set, for each training data set, it includes two classes. For example, in the training data set 1, it includes cat and birds. And for each class, it has 4 samples, so we call it as a two-way four-shot image classification problem. And when a new image come in, and it can know which one it belongs to, Thus, since we have a lot of such training data set, so we know how to classify images and can capture some universal features. And then we learn some prayers from this meta-training task after the meta-training process. Then in the meta-testing dataset, and we use this prayer to facilitate this meta-testing dataset. For example, in this testing dataset, we have a totally two novel classes. The first one is dog and the second one is otter. So we didn't say both classes are not exist in the meta-training dataset. Thus, we know how to, we can learn some universal representations and then can be correctly classify the new dog to dogs or otter. Only use a few training samples. So this is just a very simple example of meta-learning in the few-shot image classification. Then I will formulate the meta-learning problem. In the supervised learning that I think almost all of us is very familiar with the supervised learning, we have the input xt for each task, and then we have its output. Thus, we are going to find the mapping function f theta. The theta is all learnable parameters of the network, maybe the neural network or different machine learning models. Then we will use this mapping function to map the input to its output and make the prediction. In the meta-supervised learning, things may be slightly different. We still have the input and output. However, we have a new data. It's called the meta-training dataset. As the example shows that we have a lot of tasks, so each task has its own dataset. We call it a meta-training dataset. Here is task is from I equal to 1 to the totally I task. And the mapping function will be, we still want to find this mapping function, but in this mapping function, we will include the meta-training data inside in this mapping function to train together of this mapping function. Thus, this is the difference between the meta-supervised learning and the supervised learning. Okay, based on this definition, and one major type of meta-learning algorithm is gradient-based meta-learning. So in the gradient-based meta-learning, usually we regard the transferable knowledge as we showed before. We learn some prior from meta-training process. So this transferable knowledge can be regarded as a model initialization. The model initialization can be seen as, for example, if we have several layers neural network, so all the learnable parameters is consist of the model initialization theta for the gradient-based meta-learning. And then in the gradient-based meta-learning, we can still get the task adapted parameter for each task. So for each task, it has its own parameters, the phi I. And we regard the support set. Support set is for each task, it's also like a training data set. And for each task, we also have the testing data set, which is we also call it as a query data set. The gradient-based meta-learning can be formulated during the meta-training process, can be formulated as a bi-level optimization problem. We can see here are two levels of optimization. In the inner loop, we can see here, so we use the support set of each task I and to learn the task adapted parameter phi I, so using several or using different algorithms. And then after we learn phi I, we evaluate the phi I on the query dataset. Maybe it's the DQI, and then we have a loss function. We want to use this loss function to minimize the parameter theta, the initialization theta. Thus, it can be regarded as the inner loop is using the support set to update the parameter theta to get the task-specific parameter phi I. And in the outer loop, we use the phi I to go back to optimize the model initialization. So this is a bi-level optimization problem. One representative method of gradient-based meta-learning is MAMO, the model-agnostic meta-learning. In the model-agnostic meta-learning, we can see that we want to learn a good initialization, by using a few gradient steps in the inner loop. Thus, we can see we still have this equation, the outer loop. So we have the loss function and evaluate the task specific parameter phi I on the query set to optimize the theta. So in the inner loop, we use several gradient steps. So we just show one gradient step, but in practice, we can use several gradient steps to optimize starting from the theta I and to get the task specific parameters. We can see that if we start from scratch, so it takes a long time to get its task specific. This is phi. So the theta I, theta 2 star, and theta star 3 star. And if we start from here, so it is easier to get its best parameters. After we learn a good initialization, during the meta-testing time, we use the pretrained or pretrained well-generalized initialization theta star to get its task specific parameters by just fine-tuning for a few steps on the training data or support data in the new task. So the goal of memo is to find a well-generalized initialization which can achieve the task-specific parameters by using a few gradient steps. Okay, so in the traditional memo, so it's a little time-consuming to calculate the second-order gradient. Thus, it seems like we can see here if we want to optimize the outer loop, and we got this equation. If we want to start from the phi, the task specific parameters, and to go to optimize the initialization, we can see it involves a Hessian metric on the support set, and also this is first order derivative on the query set. This is time consuming to calculate the second order derivative. Here are some solutions want to use first order approximations to approximate the second order gradient. For example, in the full memo, which is also included in the traditional memo paper, and it optimized in the outer loop. Instead of calculating the second order gradient, it just use approximation by using the phi I as the task specific parameters on task I, and the performance of phi I on the query set of task I to approximate the second order derivative. And another solution is for the reptile. In the reptile, they use a simple solution that they use the order theta and minus the task specific phi, and to optimize the theta. So these are several solutions to use the first order gradient to approximate the second order derivative. Thus, it want to make the memo more efficient. Another type of gradient based meta-learning is the gradient preconditioning. In the gradient preconditioning, for example, we have maybe like we want to optimize in one space, thus that we want to go through from the theta to theta prime, and if we can control the gradient steps by using a parameterized metric and preconditioned the gradient, and we can transfer this space to another space. So in the C space, the theta will be preconditioned by the omega and change the space to the gamma. And in this space, the gradient is equal to, like, we have a preconditioned metric G inverse G, and times the gradient of gamma, and it is equal to we have a combination function that L equal to the omega. Thus, that we can find a better loss surface, and this which can be quickly to get the gradient steps. It seems that we consider the gradient trace and the model initialization. So here are an example. So in the normal gradient, we take a long way than the preconditioned gradient descent. Here are several ways for the gradient preconditioned GBML. And here we show first in the memo, we just have a gradient descent in the inner loop optimization. And another solution is meta-SGD. In the meta-SGD, we want to learn a diagonal metric which is parameterized by the parameter omega. This omega is not involved in the inner loop and only be optimized in the outer loop. Thus, the meta-SGD can be regarded as for each parameter in the model, and it has on its own learning rate, the inner loop learning rate. And also for the TNet, in the TNet, people want to insert a new parameterized metric into the model, so which is also not updated in the inner loop and only put in the outer loop, only optimized on the outer loop of the meta training process, and is fixed during the meta testing process. And the fourth one is for the meta curvature. The meta curvature is very, very similar to the natural gradient descent, and they want to learn a more complex mapping function, the B, which is parameterized by the omega. So it's similar to the meta-SGD, but it can a block level gradient preconditioning. The last one is for the Web gradient. In the Web gradient, so the people is very similar to the TNet, but TNet they want to use a linear mapping. For example, if we insert 1 times 1 gradient blocks into the 3 times 3 convolutional blocks with the ReLU activation, and this is they just do a linear transformation, but in the Web gradient they want to do the nonlinearity precondition. Here I will use the Web gradient as one example. So we can see for the input x, and the theta is used to get its hidden representation h, and phi is used for the omega. And we start from the h and omega and h2 and omega 2 to get the final representation. Here may be regarded as 2 layers neural network. And we have the parameter theta, which can be adapted in the inner loop and the outer loop. The outer loop is used to optimize its model initialization, but for the inner loop, it's used to get the task-specific parameter. And when we have the gradient, so we have the gradient fx for the theta and phi. It seems like the gradient for the theta is parameterized by the learnable parameters, preconditioned by the learnable parameters and omega. Thus, we want to have a shared web parameters, the phi. So in this time, the phi z part is without inner update. They will only optimized during the out loop optimization. So they want to wrap the gradient and change it to the another direction. This is another type of gradient-based meta-learning. Here, we show some different types of like first-order approximation and preconditioned gradient-based meta-learning. So this is the whole thing of gradient meta-learning and with some recent researches. Then I will introduce about a second part of meta-learning algorithms, the metric-based meta-learning. In the metric-based meta-learning, assuming we have a supported DS and a query data sample XQ. So for the supported, we have 5 images, and each image belongs to one class. So it seems like for 5-way one-shot classification, we only have 1 image in this classification problem of each class, and it totally have 5. And then for each data sample in the query set, we want to compare the data sample with the knowledge in the support set. We can see, so for example, this is a line we can compare with each image, and we can see this line is most similar to the line in the support set, so it belongs to the class line. There are 2 ways to compare, there are 2 key issues in the metric-based meta-learning. The first one is the comparing space. So because it's a little difficult to compare from the image level, so we usually want to transfer it to a new space. And how to define the mapping function to transfer the image to a new space or transfer different data to new space. So this is one issue. Another key issue is about the distance metric because we want to compare. So we will define some distance metric to compare these images. And the key question is how to define these two key components. Since the metric-based meta-learning usually use the nearest neighbor to compare them, so it's maybe a lazy learner. So sometimes they also call it like a non-parametric meta-learning. So one representative method of metric-based meta-learning is the matching network. In the matching network, assume we have some support samples. Here is 4 types of dogs. And we also have a query sample. Here is another dog here. And we have mapping function for the support set and mapping function for the query set. Then we map it to several vectors, vector representation, and then we compare some compare the query set with the support samples. And we got the summarization of each to get its final prediction performance. The A x hat with the xi is similar as the x hat is for the testing samples and to compare them and to get the similarity value and times the y and to got the final value. So the mapping function here is for the g theta and f theta. And the similarity measure maybe use some cosine similarity, and we can use some different similarity measures. In the traditional matching network, they focus on the one-shot learning process. So in the support set for each class, they only have one image, and in the testing set, in the query set, they want to compare with each image in the support set. How to do with few-shot learning? So it means that for each class, they have several samples. Here is another representative method for the metric-based meta-learning. The prototypical network. The goal for the prototypical network is to learn a mapping function of f5. So this is totally saying that we want to use this mapping function to map it as all image to the new space. Here we map x to a new space and find a node. And for each class, they will construct a class level prototype by use the mapped representations. The set, for example, in the class K in the support set. So we will calculate the mean value of its representation from this class K in the support set. Here is one example. So in the C1, we have 5 representation images, and to calculate the mean value of C1, and the C2 calculate the mean value of C2, and for the C3 also calculate the mean value of C3. Thus, when a new image X comes in, it can compare with the C1, C2, and C3. Thus, it can use some distance measure. And here, the distance can be used like a cosine similarity. Thus, using this one, and we can find which is the most similar prototype, and this prototype represents one class. So this is used for the classification. Here, I will discuss some more complex relations and distance measures. The first one is TypeNet in ICM-19. So they embedded to one embedding space, but they found another task-adapted projection space to project the prototype and the query image, so to a totally new space. So their goal is to find a better space to do that. The another one is for the GN, is they want to use graph convolutional neural net to do that, because we can see after the mapping, so we have several support samples and have the query sample. So for the query sample, they motivated by the semi-supervised learning, especially the gradient-based semi-supervised learning, so they can just regard it as a graph and use some message passing to propagate the information to the query set a query sample, and finally get the results. So their goal is they do for a new matching function. So they have a new measure distance. And another one is for the relation network in CPR18. So they have an embedding module, so they see the mapping function, and then they concatenate the representation of each support samples and the query samples. And finally, to get its relation score and transform it to a one-hot vector. The last one is the meta OPTNet, different from the previous one. So the previous one, like matching network, like a prototypical network, so they use the non-prematch, the lazy learner, to do the classification, such as like find the one nearest neighbor. So in the meta OPTNet, they thought that these lazy discriminators may not discriminate very well. So they want to find another one is about the meta OPTNet to use some more powerful discriminators, for example, SVM. So they want to do that by to weight the linear classify, and finally in the test examples, and they can got the score for each class, and finally do the optimization process. Okay, so here I discussed about the gradient-based methods and the metric-based methods. It's just a briefly summary and compression. So in the gradient-based methods, it can handle different problems. For example, regression, classification, and reinforcement learning, and it's a little computational expensive. So in the metric-based methods, so it's very simplified and entirely feed-forward, no inner loop updating, and it depends on the distance metric, and but it's the current version is limited to classification. Then I need to mention there are several different types of meta learning algorithms, such as memory based and also neural process. So, but I just may put two very important types of meta learning methods here. Then I will mention two key challenges of meta learning. The first one is task heterogeneity. In the task heterogeneity, we can see that previously we learned a globally shared model parameter initializations in the gradient-based meta-learning, for example, like MAMO. So the learned initialization is shared across all the tasks. It seems like in the right figure, we have a theta, and to go to the theta and global shared theta, and to transfer it to a global shared theta, and which it can be fit to each task. However, in our human being, sometimes the tasks are very different because we can learn different tasks, and our human being can organize this knowledge to different maybe groups. So we can see for the linguistics courses, we have different courses for the linguistics, and we have different courses for the physics. And we also have some courses from math. And in our human, we can organize these courses to different groups. So we know this course is linguistic, this course is math. Then there are a new task coming in to we want to learn the group theory. So the group theory is obviously very similar to the math courses because it's high-level math courses, and maybe also have some similarity, have some correlation with physics, but less correlation with linguistics. Our question is, if we learn a globally shared meta knowledge or the meta model, so it seems that all tasks are useful to help the group theory. However, things may be different because obviously the linguistics may not help to the group theory. Thus, our goal is to find some hidden relations across all the historical tasks. And for a new task coming in, it can quickly find which is the most relevant knowledge, and then use this knowledge to facilitate its learning process. One method called HSML is proposed in ICM-19. So the goal of HSML is that we have a global shared theta, but we want to get some clustering structure. So the theta will be reformulated as theta 1, theta 2, theta 3 for different groups. So we can see the theta 1 is fit for task 1, task 2, 3, and theta 2 is for task 2, and theta 3 may be useful for task 4. So in the HSMLC want to balance the generalization and the customization. So in the generalization, it seems that within each group they have some general knowledge, but across the different groups they have some customization knowledge. So the goal of HSML is to organize tasks by the hierarchical clustering structure. And also it can adapt the global initialization to each cluster of tasks. Here I will introduce each part separately. The key idea for all the task heterogeneity research is to learn the task representation, because only if for our human and we know of these courses is a group theory, so we do not know the details of these courses, but we have a brief introduction of these courses. So this is similar as a task representation. In the machine learning, so it's a little difficult to learn the task representation because we want to represent each task as one vector, for example. So this vector covers the specific knowledge of each task. And our motivation is to aggregate all the samples in the support set, because for each task it comes in and we know the support set. So we want to aggregate these samples in support set to get its final representation. Here we can see for task I and the support set we have 8 images, and we have a mapping function to map it to a new space. Then we want to design an aggregator to aggregate all these samples to a new vector. In here, the autoencoder is proposed for the aggregation. So for the input, we input all the data samples and then use the autoencoder, and then for the reconstruction area. So the reconstruction is used, maybe it's very useful to opportunity to get some constraint to learn the task representation, because in the meta-learning sometimes we do not have any prior knowledge and we totally learn from scratch. One task come in and it come out, so no information will be saved. And the reconstruction area can help us to increase the learning stability. Okay, after we learn the task representation, we can see the task representation can be used to represent this task, so to reflect the some task similarity. And then it will be used to interact with the task clustering structure. The goal for the interaction with the task clustering structure is to enhance the task representation. So for here we can see we have a task representation, and then this is the clustering structure. So for each node it has its own representations. This representation may be represent one type of knowledge of this task, and we have several representations, and then it can choose the similarity path of it and to enhance its representation. Thus, after the enhanced representation, it covers the knowledge from the task, also have some historical memory knowledge. After that, we have the enhanced representation and the original task representation. We use them to adapt the knowledge to customize the meta-learner. What is the customize of meta-learner? For example, here we show a memo structure. It's a global meta-learner. We have a global shared theta, and then it can be adapted to different theta value. And then if we do a task adapted meta-learner from theta, and we can go one step to customize it for the new initialization, and then do the task adapted steps. To do that, so we use the task representation and map it to a new space and to design a parameter gate, and then use this gate to customize it or to modulate the model initialization. Thus, the HSML can distinguish different groups of tasks and to customize the model initialization. The question is this way can achieve better generalization? Assuming we have k clusters of HSML. Here we show this equation. The theta CLT can be just like a linear combination of the theta 0. And then with the generalization bound of the f theta of the transfer knowledge, it can be regarded as this one. And for the memo, so for each k and bk equal to I, so equal to I times I divide k, because so this is a mistake, sorry. So, and then for we want to show that if we can find a bk, that the theta 0t can find a tighter bound of that, so it would be better. One very simple way to prove that, to show the existence, is that just go one gradient step from the starting point, and then from the update from the one gradient step. And finally, we can show it can be regarded as this part can be used to represent the bk. So, and we can find that we can definitely find one bk which can will exist, and the memo will and the HSML can achieve the tighter bound of the generalization. Here we show some qualitative analysis of HSML. Well, we can see we select the 4 single family functions: the sine, line, cubic, and quadratic. So, for example, in line, we have ax times b, and different combination of a and b will be considered as one task. And this is the k-short problem, so k samples are used as meta training, so for to construct the support set. And here we can see that the HSML can achieve better generalization and can distinguish different shapes. We also show a similarity mapping function for the first level of clusters. Let's show one example. So for the cluster 1, and we have the sine and the quadratic 2 that both activate the cluster 1. So we can see that the sine and the quadratic 2 will be very similar. It's like a wave. And also give another example is for the C3, is for line and quadratic 2. So the line and the quadratic 2 both have a very similar. The quadratic 2 have a similar shape of line, and which is with the positive slope. And the difference will be the quadratic 1. The quadratic 1 will be activated C4. So quadratic 2 and quadratic 1 also. The quadratic 2 and the line also activate C3. So this is several examples for the qualitative analysis of HSML. Let's look at the clustering structure. So in this work, so it can handle the clustering structure very well by using a hierarchical task clustering. However, the hierarchical task clustering relies on the handcraft design, and it cannot model very complex relations because it just covers the clustering structure, and there are no relations between different clusters. Okay, let's show another example. So to improve the cluster structure and to avoid the handcrafted design, there will be a new structure of each, which we call like a meta-knowledge graph. Different from the clustering structure, the meta-knowledge graph include the relations between different groups or the summarization of tasks. You can see there are strong correlation from physics and math, but weak correlation from the linguistics to physics and linguistics to math. To achieve this, in ICLR 20, so the AMO is proposed to achieve this goal to automatically learn the structure. So the key idea of AMO, the first is they want to structuring samples as a prototype-based graph to model the relations across different samples within one task. And another one is to as a modeled prototype-based relational structure can be used to query the constructed meta-knowledge graph. In the meta-knowledge graph, the knowledge will be used to formulate the meta-knowledge graph, and they are also include the correlations within this task. Here we show, like in the AMO, that the task organized representation. So there are prototype. First, we have training samples, and we want to construct the prototype. And then, based on the constructed prototype, we can construct a prototype-based relational graph. This prototype-based relational graph includes the knowledge we see of these prototypes, so based on the prototype relations for the prototype-based relational graph. Here I give some more detailed explanation is that compared with we represented all the samples and aggregate all the samples to one representation. So if we first do a prototype the relational graph, we can better construct better use the information within one task, within the support set, because we definitely know the labels of it, and we can construct it together. Later, here we have a prototype-based relational graph, and we also want to construct the meta-knowledge graph. The meta-knowledge graph is used to like a clustering structure, and we have the link across the clustering structure based on the clustering representation, and the link will be also learned and also changed during the meta-training process. And we want to propagate the knowledge from the meta-knowledge graph to the prototype relational graph to enhance the task representation. And the prototype relation graph will cover more information of this task. To propagate the information from the meta-knowledge graph to the prototype-based relational graph, here we will construct it as a supergraph. The supergraph consists of nodes, two types of graphs, and these two types of graphs consist of the nodes of the whole supergraph and with the links across the graph. So there are three types of links. The first link is based on the prototype-based relational graph, and the second type of link is in the meta-knowledge graph. And finally, the link is a cross-link between the prototype relational graph and the meta-knowledge graph. And then the information can be propagated from the meta-knowledge graph to enhance the representation of prototype-based relational graph. With the enhanced representation, we can find two autoencoder aggregators. So to aggregate the information from the original prototype knowledge, and another way is to aggregate the information from the prototype-based relational structure, and then this is for the original representation for each task. And before we calculate it, and it can also reduce the complexity of aggregators. We did not use too much samples. We can just construct it as a prototype. And then the prototype can also be used in another aggregator to aggregate the enhanced representation of the prototype relational graph. This enhanced representation is used from the meta-knowledge graph. Thus, after that, we have the task representation and use the task representation to modulate the model initialization theta 0. Similar to the previous work, and this modulation can also improve the generalization. But in this part, we can it covers covers the more complex relations and more detailed relations like prototypes and meta-knowledge graph. And it seems that the meta-knowledge graph can be automatically constructed, and we did not need to handcraft the design. Maybe it's for the number of layers in the clustering structure and for the number of nodes in each layer. So just put it automatically to construct the meta-knowledge graph. Sure, in this part, we show briefly results like the quantitative results in the few-shot image classification. In the few-shot image classification, we construct 4 groups of images. Like each part can be regarded as mini ImageNet or OmniGlot for the few-shot image classification. And there are 4 groups: bird, texture, aircraft, and foundry. And each group we add 3 different filters. So totally 12 task groups has been constructed, and we compare with the task-specific models, the HSML and the ARML, to compare with MAML, and also compare with ARML with the HSML. So we found that if we can automatically construct the relational structure, it can work very well, and it can cover the most knowledge, the most types of knowledge in this work. So this is the first way to tackle the task heterogeneity. I show two representative methods. There are other task-specific meta-learning models. The first idea is similar to the previous HSML and ARML, so use task conditioning. So to customize or modulate different tasks by using some task representations. So in the ICLR 20 and the NIPS and different NIPS paper, and they also focus on both gradient-based meta-learning and focus on the metric-based meta-learning. And another idea is to use MAML with the directorate process mixture. So they want to use Bayesian to add some prior on each and to model the whole process, and to encourage the model can distinguish different groups of knowledge within the tasks. Okay, then let's move to the second challenge, the meta overfitting. So the meta overfitting is that we want to find the overfitting in the meta-learning process. Here are the typical way of the meta-learning process. We have a initialization theta 0, and we use support dataset to do the update and to get phi 1 to the phi I as a task-specific parameter, and use the query set to go back optimize. So in the out loop, optimize the theta 0. And also in the meta testing, so we use the theta learned optimal theta 0, and with the target task t and its support set, and to get its the phi t is the task specific parameter, and finally use the query set to evaluate the performance. So there are two types of generalization in the meta learning. The first one is task generalization. So we also see an inner loop generalization, because maybe sometimes theta 0 may cover a lot of parameters, and we use the support set, but the support set only covers maybe a few data samples. So it still will overfit in the inner loop. So it may have a negative effect on the inner loop generalization. So this is a briefly generalization in the traditional machine learning. And different from traditional generalization, there are another generalization we call it as meta generalization. In the meta generalization, so different from the original generalization, the meta generalization seems that it is more like a overfitting on the tasks. So because if we overfit all the tasks in the meta training process, we totally memorize all the tasks in the meta training process. So it will be affect to the generation performance of the meta testing task. In the meta learning, the overfitting in both the inner loop generation and inner loop and the meta generation will affect this generation ability. Here, we show some representative way first to overcome the task overfitting. The task overfitting, it means the overfit in the inner loop. One typical solution is because since we only have a very limited number of data, and if we and the maybe low level layers can also learn some universal representation. So a simplest way is to whether we can reduce the number of parameters for the inner loop, because maybe we have maybe 20 or maybe less than 100 samples. So it's a little difficult to optimize too much parameters. So we want to reduce the number of parameters to elevate the task overfitting. So one way for it is for the caveat in the ICM-19. So they will introduce textual parameters phi. So in here we have some parameters and some representations, and with theta as parameters, And if we increase some representation nodes to get the next level representation, and we only updated the parameters regarded correlated with phi, so it can significantly reduce the number of parameters for the inner loop. So it will improve the generalization ability. Another way is more powerful way is to just update the last layer. So in the head layer, so this work is published in iClear 20, and in the last layer, so we only do the input in the last layer because usually in deep learning, the low level layers for the universal representations do not need to be changed because they have some universal representation and can learn some invariant representations. Thus, we only change the last layer, so the head layer representation, and to do the adaptations on the head layer. So this is two ways to overcome the task overfitting by reducing the number of parameters. Another type of research focuses on can we inject some adaptive noise. So it's motivated by the dropout, but they want to learn how to perturb the features during this time to improve the generalization. Here we see that they introduce another parameter phi, which is also learned in the out loop. And for each x is for the input. For each input, they use phi to learn some noise, and this noise will be injected to the convolutional layer. And after they injected to the convolutional layer, they have some for each layer they have some noise generator, and it seems that they introduce more data samples or add some perturbation on the previously features. Their solution seems that they work very well in compared with Memo, so they have a better boundary. So we have several data samples, and this is for their perturbed training, and it seems also they increase more samples and with the perturbation, and they will find a better boundary. So this is also a way to overcome task overfitting, but from introduce more noise, to perturb it, and it's motivated by the dropout. So they call it a meta dropout. Okay, so here we show some works of the inner loop generalization. So the inner loop generalization is also very important for the meta learning. But in the meta learning, the most important overfitting problem and much more challenging overfitting problem is meta overfitting, which affects the meta generalization. Because if we memorize all the tasks in the meta training process, how we can improve the meta generalization in the meta testing process? Here we show one example. So this example is from the drug activity prediction, and we can just mention that the mean R square and the high means R square means the high performance. We show this figure because that we want to find which one is the most important items in the meta generalization. Because we use the query samples in the out loop to optimize the theta 0. So is it memorized for the out loop? So it seems in some cases, so it's correct. And we can see this is the meta training support for the green line, and this is for the meta training query. So it seems the meta training query, the performance will be very, very high. And it seems that during the meta training process, it totally memorizes the query set. And it consists of the inconsistent behaviors of the learned initialization. So we use the initialization on the meta training query and the meta training support. Thus, it causes the meta overfitting. One solution to solve the meta overfitting problem is to passively impose some regularization. One example is Tamo, published in CPR 19. So in the traditional memo, we have the first items as the loss function. So we want to have the loss on the theta I, is that we use theta I evaluated on the query set. But for this work, they want to encourage the similar behavior across tasks. Thus, they introduce an inequality measure to do that. So this inequality measure is to encourage the similar behavior of the parameter theta, so the initialization on different tasks. So to find it more to make it more similar, and then to avoid that some meta-learning overfitted in some tasks, some major tasks, and ignore some other tasks. Okay, so another work is published in ICLR 20 is that they also show one examples. So we have the meta training task 1, meta training task 2, and the meta training task 3. And it is ideal way is in the meta testing process is it can adapt to the validation data to the meta testing task. However, if we memorize it during meta training, it cannot achieve good performance that affect the meta generation. It memorizes all the meta training data. To avoid this, they want to maximize the mutual information from the training source samples. The D is for the all meta training tasks, and Y star is for the meta testing labels. So they do not want to memorize all the knowledge in the meta training is the D, and they want to use the X star, so the meta testing task, the feature of meta testing task to benefit the process of the Y. So they want to maximize the mutual information. By maximizing the mutual information, and they impose a regularization on it. So they split the whole network to the fixed layers and adapted layers. And in the adapted layers, they want to make to minimize the KL divergence between a normal distribution. The P is a normal distribution for the parameter theta. It seems like it also is similar to the L2 norm, just add a regularization on it. So this is just another solution to overcome the meta overfitting. So these ways propose some solutions for the passive imposed regularization on it. There are one question: is there any active way? So in the active way, because to overcome the overfitting problem, so one way is to introduce some regularization, and another way is to actively add more data. So one way is that can we use more data in the meta-learning procedure? And because we have a support set and a query set, and it seems in previous figure, and the queries can overfit the query set, but performs very bad on the support set. So our question is, can we use the support set in the out loop, also use support set in the out loop to optimize theta? A simple way is to just simply combine the support set and the query set to go for the out loop optimization. However, things may be difficult because we can see that the support gradient norm and the query gradient norm is totally different. The support gradient norm is almost in the learning process. The support gradient norm is very, very small, so it's a very bad to learn a better support gradient norm. Thus, if we simply combine the support set, things will not change too much. Thus, the meta mix is proposed, motivated by the manifold mix-up and the mix-up, and to use a linear combination of the support set and the query set to construct a new data set called the mixed data set. So in the mixed data set, so we have a linear combination of support and query, and for the label also have the support and query. So we use it to replace the query set to optimize the parameter theta 0. Thus, it will incorporate the support and the query set together. The question is, can the meta mix promote the meta generalization? We show some briefly analysis here that if we use some Taylor expansion and also use some first order and second order approximations of gradients, and we can get performance is that here is just for L is for F star to show the loss function of if we do it on the f theta 0 is for the model initialization. And since the mu is for the learning rate, it's a very small value, and we miss the second term and only use the first term, and to analyze its property. And in the classification, after using the meta mix, and we have a mixed data set, the D mix, and it seems there are knowledge distilling across support and target set. So it means that the knowledge will be distilled from the support to the target and the target to the support, which has been proved can improve the generalization ability in the previous work. And also in the regression problem, we show, so this is the regression loss function. And in the regression problems, we can see that we assume that the features, the features may cover some bias because support and query set are all sampled, so they both may have some bias of it. And it seems like in this figure, we show a linear function is for the gray color and some support samples and query samples. And also we can see that we recover the linear function by using the meta mix. So by using the meta mix, we can recover the linear function of it. Because if we only use the query set, we cannot get a non-biased the model. By calculating the analytic value of the memo and the meta mix, so we can find that the memo will be overfit on the query samples, but meta mix can without overfit on the query samples, so it can recover the linear function very well. So it seems like a red fitting curves, so it recovers the linear function very well. Okay. So both in the classification and regression problems, we just briefly show that the MetaMax can promote the meta generalization. Let's see some empirical effects. In the drug activity prediction, let's see, before the MetaMax, we found a very large gaps between them, between the meta training support and the meta training query. Also, there was still a gap between the meta validation query and the meta validation support. However, when we use meta mix and then test it on the meta train support and the meta train query, the gap is very small, and it reduces the large gap to the small gap, and also improves the performance of the meta validation query set. So empirically. So it seems that MetaMix can improve the performance of the meta query to improve the performance of the meta learning problems in different applications. And another empirical results is shown in the image classification. Both omniglot and mini-genet has been used. And here we show some different ways to overcome the meta overfitting and the overfitting in the inner loop. And also, we apply the MetaMix on the different meta-learning blackboard meta-learning algorithms, so the MEMO, MetaSGD, TNet, and ANO. And we can see on different, when applying the MetaMix for despite the different blackboard algorithms, we can still achieve better performance. Also, in the right figure, we can see compared with MEMO, which only covers some support samples and query samples, and the MetaMax can find a compact representation between the support and query, and also achieve a better decision boundary. Thus, up to here, and I introduced two types of meta-learning algorithms: the gradient-based meta-learning and the metric-based meta-learning, and also involves two challenges: the task heterogeneity and the meta-learning in the current meta-learning research. So finally, I will show some applications of this part, some meta-learning applications. So in the meta-learning applications, I will majorly introduce two applications. One is from the e-commerce scenario, and another one is from spatial temporal prediction. And then I will introduce other parts of applications. The first application is from the e-commerce application. Is in the e-commerce scenario, the 聚划算 in Alibaba. So in the 聚划算, so they want to display some market segments on their platform. So different market segments will be put in the platform, and people will use it to choose these items belong to a specific market segments. But due to the capacity of the platform, because we cannot put all the items in the platform, so it's a little difficult to do that. So how to choose which item should be put in the platform? We want to estimate the market demand. So if we can better estimate the market segment demand, and we can better, the manager can better choose which one can be displayed in the platform. Different from the time series prediction, so in the market demand prediction, we use historical records to predict the target demand value in a feature time step. So if there are a gap, the TG and a gap between the historical records to the target demand value, because there are time gap between the downstream and upstream the items. So they want to get some items from the other platforms, and to finally to use it for the to predict the demand value and to optimize the platform. So there are one scenarios. So if whether we can know which items may not have records, so if they do not have any display, so it means they do not have records. And if we put it in the platform but nobody click or purchase, it means they have the purchasing value will be zero, the demand value will be zero, but it still has records. Let's see. So we collected more than 4,000 market segment and calculated its frequency. We can see it's a totally long tail distribution. So a lot of items may not have enough data to make a good prediction. So why is it important to make the prediction for the market segment with the data inefficient market segment? So because if the market segment without having enough data, so it may do not have the display opportunity, and it's also difficult to collect data, and it will also cause a data insufficient segment. It's just a vicious circle, so it's very bad for the e-commerce platform. But why the data insufficient segment is very important? Which segment will be data insufficient? Let's see several examples. First, some items are always important, like rice and oil. People will always use it to purchase it in different seasons. So like both of these items are totally data sufficient. But another type of items is for the seasonal important. So it may be less data insufficient in different seasons. For example, in the rose, and people usually purchase it on the different holidays, and for the jacket, people may purchase it in different seasons, in a specific seasons. And the third one is definitely a low quality item, so data is insufficient. For example, so the people purchase some typical items, some typical batteries in some specific devices, so it's a little difficult to do that. So few people will purchase it on this platform. So this is a low quality item. We can see some seasonal important items may be data insufficient, and low quality items may also be data insufficient. For the platform, we do not want the low quality items to put in the platform, but we also want the seasonal important items to put in the platform. Thus, segments with limited records is not equal to the low quality records. We want to improve the prediction performance of data insufficient segment, and if we can predict it very well, and we can improve the performance, the downstream performance, to put them on the to display them in the platform. Okay, here in this work, we just use the gradient-based meta learning as a black ball, and we also consider, in this scenario, we also consider the relational aware models. And there are two types of relations are considered in the meta learning process. The first one is the data-driven relation. As we previously showed in task heterogeneity, that different segments may also have some correlations within them. For example, the green card, and we will be more close to the rose and will be less close to jacket. So this is data-driven relations. So it's totally from the purchasing records and maybe from the timeline, something like that for the data-driven relation. And another part is that these relations can be built from the user records, which inexpressly to represent the relations across different market segments. For example, we can see the users purchase these items maybe together or concurrence in one a short time. So they purchase different items together. We can see if users tend to purchase two items together, they are more close that these items may have strong relations. So we build these graphs from the user records. Two types of relations are used to improve the meta-learning models in this work. Let's see the experiments. So we have collected 4,000 market segments in Junhuasuan and use and to improve the data in sufficient market segment. Here we show some baselines. The first one is mixed XGBoost. So in the mixed XGBoost is just mix all the source tasks, the data set of all the source tasks, and feed it into the XGBoost. And for the fine-tune, so we mix all the source tasks and fine-tune the deeper model. In this blackboard deeper models, it covers the seasonal information and the closeness information. And for the memo, this is mostly use the meta-learning methods, which will include the inner loop update. And our method can achieve the best performance. Also, we put the model in the online in the Juhuasuan platform, and we construct an online A/B testing with the similar page view and unique visitor, and our model can achieve more weekly orders. So thus, we can see that when we introduce the relational knowledge and use the meta-learning in the market segment demand prediction, we can actually improve the performance in the platform and improve the quality of the platform. So this is the first example. In another example, this is very correlated to the spatial temporal prediction. We use the knowledge for the taxi demand prediction. In the taxi demand prediction, as JC said in the introduction, so if we want to analyze the taxi demand to predict the taxi demand, but we cannot find too much data in Boston because when we entered in taxi in Boston website, so we do not have any data. Here, we just want to transfer the knowledge from the data sufficient cities to improve the performance in the data insufficient cities. In the data sufficient cities, we choose Washington, D.C. with 7 months, New York City with 6 months, and Porto with 1 year data to facilitate the learning performance of the Boston with 1 day data. Only with 1 day data, so it means that we do not have too much, but for 1 day, we can also improve the performance. The taxi demand prediction performance can be regarded as a spatial temporal prediction value performance. Let's see the left figure. We have a Manhattan city, and in the Manhattan city, we want to split it to several blocks, and each block in one-time intervals taxi demand, we regarded it as a value of taxi demand. Then it seems that we given the several values from 9 a.m. and 10 a.m. We want to predict the spatial temporal value in the next steps or next time interval. Usually, we also use the meta-learning on the taxi demand prediction because we want to transfer the knowledge from multiple cities to a new city. In the base learner, we use the convolutional neural network, which can capture the spatial information from one region, the nearby spatial information. And another one is for the LSTM is just to capture the temporal information. We choose the performance of the IMSE as the prediction error. If we only use the target data set, so we only have a few data samples to train it. And if we mix all the source tasks and to fine-tune it, and it can improve the performance. So the transfer can increase the model the performance. And finally, we use memo as another baseline to improve the multiple fine tune. In the last, we use our method in the triple W paper. So this says that our method can further improve the performance on the memo. The question is why our method can do that. The key major contribution is that we consider when we do a transfer, so from Washington DC, New York Proto to transfer knowledge to Boston, and we consider some patterns within each region. For example, the region in the New York University and Harvard University, and we can see the text demand value may be quite similar. For example, the text demand value around the New York University may be higher in the afternoon or high at night. So it's similar as the Harvard University. These patterns is quite general because it can be transferred in different cities, because different cities always have some residential areas, cities has some patterns, and the working areas also has another type of patterns. So these types of patterns can be regarded as such. So in different cities, it reflects the region functionality of these regions. We want to use this pattern knowledge to enhance the representation of the target city. So for example, we found some similar patterns of New York to enhance the representation of the Boston. So these patterns can also be transferred, and we construct a pattern-based memory to do that. In the memory, so each row of this memory encrypts the one type of pattern. So sometimes this pattern will be totally zero, maybe a region that do not have too much person, and also have some working area and residential areas. So these patterns this memory encrypts the pattern information. Thus, by using these patterns to enrich the representation, our model can improve the performance than memo. So up to then, I show two applications of meta-learning applications, and here are more applications. So the first one is for the meta translation in EMLP 18. So in the meta translation, that people use the knowledge and to transfer the knowledge to benefit the translation with low resource machine translation. And another type is for the relation extraction. In the relation extraction, that people use that a field labeled sentences and to want to do the classification of the relation. And another one is for the global relational graph is be covered as a prior. So this they construct the graph-based prior, and also use the Bayesian prototype to get its likelihood, and then it combines them to get its posterior and use the Lagrange dynamics to optimize it to get the final prototype factors. And in AAA 20, and we propose a model for the graph node classification. So in the graph node classification, we have a lot of source graphs, and then we want to benefit the learning process of the target graph. So in this part, so we consider both the local graph information, the local information, because for each class we only have a few nodes, and we construct a very small graphs, a small prototype-based graphs. So this is a prototype graph, and use the prototype graph neural network to get the graph structure prototype. Also use a hierarchical graph representation gate to represent the whole graphs and distill this knowledge to customize the graph structured prototype. And finally, for the text classification in EMLP 19, so we have a lot of classes, and for each class we have several samples, and in these samples, in the traditional prototype construction, so we calculate the mean value of its samples. But for the text, so maybe it's maybe more sensitive to the outlier, so they want to choose which is the most confidence ones within each class. So in this class, there are maybe 5 samples. They want to choose the most confident ones, and then construct the class vector. Finally, use the query vectors to quote the relations between the source vectors and get some relational scores. Finally, to get some one hot vector. Okay, this is all things in the auxiliary tasks. JC introduced the transfer learning and multitask learning. I introduced the meta learning and some applications of that. Here then, the Guanjie and Xiaowei will introduce another one. So they want to transfer the knowledge from the domain experts, because in the domain experts they also have some knowledge to transfer, and to also tackle this problem of learning with small data. Thank you very much.
Hello everyone, welcome to the second half of our tutorial. I'm Guanjie Zheng from Shanghai Jiaotong University. Now we are going to talk about how to utilize domain knowledge to deal with the learning with small data problem. So far, we have already covered how to use the knowledge transfer from the auxiliary task to overcome this small data issue. Then is there any other way to guide this learning process? Actually, yes. Now, let's first take a look at a really simple example. Say we are going to predict the trajectory of a ball. Then, as a data scientist, what will we do? Usually, we will try to throw the ball as many times as possible so that we can try to collect as many data as we want. Then we are going to build a machine learning model which takes the feature like current position, mass, or force about the ball and try to predict the next position as a label y. In contrast, then how would a real scientist try to solve this problem? Here I gave a really simple solution from the Newton Physics for Babies. This is a really famous book for the babies. So how would they solve this problem is that they usually will try to use Newton's first law, Newton's second law, and third law, and try to build up the equations to derive how would this ball move. They are thinking about that they want to solve all these problems in the road using the Newton's law, like predicting the ball trajectory, or even try to go to the moon. Well, that's a really good ideal solution, but in the real world, sometimes this might be inaccurate due to many other reasons, like uh, if there is a wind or the bouncing of the ball is not ideal. So, is there any way for us to try to combine those two successful models, like the physics model and the and the machine learning model? Well, this becomes a really general question. Here we give this general framework, like if we have a machine learning model like this, which takes the feature X as input and predicts the label Y, is there any way for us to use the domain knowledge model to help us improve the label Y to a better solution? Next, we are going to actually introduce several different methods in doing this way. First, we are going to take a look at some really simple methods, like we can try to use domain knowledge as pre-processing, like using knowledge as feature. Some researchers in recent years try to propose a model like this. They are going to use features from the dataset uh, and first use a physics model to predict the y. Then they are going to concatenate the predicted y and the original features into another machine learning model. Then finally, they are going to get the final prediction y hat. Well, another way actually we can also do is that we can use the domain knowledge as a post-processing step. For example, if we are going to predict the structure of a crystal, uh, from the domain knowledge perspective, some scientists might try to predict or calculate the power or say the energy of each candidate crystal structures. However, there are too many candidates so that it's really expensive for them to calculate them all. Therefore, some scientists try to propose another idea, which is we first use available data like uh, uh, the proportion of different chemical elements in this uh, material to predict the possible candidates, which will give us a short list. Then the domain knowledge can be used to further prune this short list to calculate the most possible structure. So in this way, actually, the data science model and the physics, or say the domain knowledge model, are used in this two-step process. Besides this, actually, there are several other categories of methodologies trying to use domain knowledge to help machine learning models. So next, we are going to first talk about how to utilize the loss function design to incorporate the domain knowledge. Let's first take a look at what normally in machine learning model the loss function is like. Here, usually we have a machine learning model like this, which takes the feature x as input and predict label y ml. And we try to calculate the loss function like this. We usually calculate it using yml minus y2. And we try to minimize this gap so that we get a better machine learning model. Then our first idea actually comes from the residual modeling idea. So given all this machine learning model and domain knowledge model, which generates the ML prediction and domain knowledge prediction correspondingly, is there any way that we can try to utilize this YDK, which is the domain knowledge prediction, to help our machine learning model? Yes, it is. So here we just try to utilize the domain knowledge model prediction as part of the final prediction. And we hope that we can use the machine learning model only to predict the gap between the domain knowledge model and the true prediction, which is we actually use the loss like this, where the ML only try to minimize the gap between domain knowledge model and the ground truth prediction. So that's why we call this residual modeling. Instead of directly predicting the y true, we are now trying to predict the residual. Well, is there any guarantee behind this? Actually, we have already tried to work on a paper about this, and we have already proved that this kind of residual modeling is better than directly using a domain knowledge model, or better than directly using a machine learning model. More details about this paper will be on arXiv soon. Here we are going to use an example to describe how we can utilize this residual learning structure to help our prediction. Say we are going to predict the temperature of different places on the Earth, then from a domain knowledge perspective, sometimes people are going to believe that most of our energy on the Earth is coming from the sun. So probably the first step is going to calculate the heat that is from the sun. Then the second step is going to calculate above all the heat we get from the sun, how much have we absorbed, or how much have we reflect. Then we are going to need the date and the latitude of our position so that we can calculate the angle of inclination of the sun. By doing this, we are going to build a coordinate system so that we can calculate how much energy in total we absorbed. After that, we are going to utilize the Stefan-Boltzmann law to calculate how much temperature change is induced by the absorbed energy. So this is a three-step process uh, from a domain knowledge perspective in order to calculate the temperature of, of one place. Then how should we combine this with our machine learning model? So basically, our machine learning model will also take the month, year, and location of the data points and try to predict the temperature. While the domain knowledge model actually, based on all the three different series, they are going to also take similar features and predict the y. Then we are going to combine those two predictions into the final prediction, like we mentioned before. Well, how does it work? You might be really curious. So here we just give a really simple comparison of three different kinds of models. By directly using domain knowledge model, well, you can reach an RMSE in terms of Celsius degree at about 8. Well, by directly using machine learning model, well, you can improve a little bit to over 6. And by further combining those two, you can actually reach a really small RMSE, which is close to 4. So that really shows how this combination of these two parts help in our model building. If you are interested in more detailed results on this dataset and about other methods, other datasets, you're welcome to visit our paper, which will be on arXiv soon. Well, after that, actually, we also did a case study on the predicted results to show how does those model building process helps. Here, we first show the ground truth temperature of the global of the globe. So we can see that actually they vary a lot in different locations. And here, we also try to show the other prediction results by different models corresponding by the combined model, by domain knowledge, or by the machine learning model purely. We can clearly see that actually the domain knowledge model can really help us try to get the mapping between the latitude and the temperature. Well, although the machine learning model can reach a relatively smaller area than the domain knowledge model, they cannot capture the trend mentioned above, which is the mapping between location and temperature. Well, by combining those two, actually our combined model can overcome the high error in domain knowledge and also incorporate the trend. Well, besides the previous mentioned method, actually there are some other methods trying to revise the loss function. Let's go back to this machine learning model and domain knowledge model paradigm. So given those two models, is there any other way we try to combine them? Yes. So by directly modifying the loss function, we can try to generate a combined loss where the first term is actually about the prediction of the machine learning, and the second term is about how this prediction fits the domain knowledge. So here we use G as a measure of the consistency between domain knowledge and predict label. And we use MDK as a transformation of the feature X given the domain knowledge. So basically the second term will try to measure how well your predicted machine learning data fits the domain knowledge principles. Next, we are going to give another example on this. Here, we are going to observe a lake water system. If we are going to predict the temperature of the water in this lake, there are a lot of factors we need to observe and consider. For example, like all the meteorological features, like the snowfall, the temperature in the air, the rainfall, the solar radiation, all these factors they will have a great impact on the temperature change of the lake water. If we are going to build a pure machine learning model based on this might be a really challenging task because it's a really complex relation. However, we know that the temperature change of the lake water never comes from nowhere. So if we try to think about this problem in the energy conservation perspective, we know that the energy must have a source and have a target. So if we try to represent the incoming energy flux of the lake water and outgoing energy flux of the lake water, we will have the confidence that uh, their difference must have a relationship with the temperature change of the lake water. Therefore, we try to build, uh, actually, we can try to refer to this SDM paper from Jia, and they are introducing how to utilize this energy conservation law to help the prediction of the temperature change. So specifically, they are going to build this lake thermal energy budget, which basically try to model the mismatch of the F out and the F in. So we have already talked about the difference between these two. Actually, is because of the actually leads to the temperature change. So based on our domain knowledge, actually, it's easy for us to build laws like this. So basically, we try to minimize the mismatch between the temperature change representation and the uh, energy flux difference. So this domain knowledge based loss is going to be combined with machine learning prediction loss, and we are going to minimize linear combination of this. So how does this method actually perform? So here we give a very simple comparison, which is also from the same paper. So the authors actually compared three different methods where GLM is the physics model and RNN is definitely a typical machine learning model. So they compared those three models where PGRN is their proposed one. They compared these three models in terms of the RMSE and also the energy inconsistency. So in terms of RMSE, actually PGRN can reach the lowest RMSE, and also PGRN can reach much lower inconsistency of energy than the pure machine learning model RNN. So if we try to observe the inconsistency on the time scale, the authors also showed us that if we plot all the G, which is a representation of the temperature change, and the representation of the energy flux difference, ideally we will hope these two curves uh, overlap with each other in the time scale. What we observe in the physics model, actually they almost overlap with each other. While in the RNN prediction, although we can reach fairly low error, this prediction actually violates this kind of physical rule because the temperature change and the energy flux doesn't match. Well, in the PGRN predicted result, actually those two quantity match well with each other. So in the previous example, actually, we were talking about how to utilize the label data to construct the machine learning loss and the domain knowledge loss. However, if you notice that actually the domain knowledge loss actually has nothing to do with the label itself. So actually, the authors also, the researchers also come up with an idea that can we use the unlabeled data to further help the prediction of the machine learning model? The answer is yes. Therefore, those researchers further try to construct the domain knowledge loss based on the unlabeled data. So through this kind of methodology, actually, we are going to have a lot more data than previous example to use in the real prediction problem. Then how should we use this? We are going to still use the previous example, but use a problem as in a different setting. So the authors of the WRR paper actually try to set up the problem like this. If now we have the data in some coldest seasons, and we want to transfer the model to give a prediction in a warm seasons, then can we try to utilize the unlabeled data in the warm seasons to help the prediction? So if we try to visualize the temperature, which is a heat map in the background, and the seasons in the shadow, basically we have the data. We have the data, basically the training features and the label in the white area, while we don't have the data for the training labels in the shadow area, which is the warm seasons. So the authors illustrate us how to utilize the unlabeled data in the shadow area to help the prediction of the machine learning model. So they compared three different methods, which GRM is a physics method, RNN is a machine learning model, and PGRN is their combined model. So compared these different methods using RMSE, definitely PGRN get a much lower RMSE. Please note that the RMSE is going to be smaller, going to be larger on this way. So definitely PGRN reached the best result under this train and test, same training and testing setting, which basically means they train on the coldest season and test on the coldest season. Well, if we change the setting to a different setting, like if we train on the cold seasons and test on the warm seasons, then all the method is going to perform a little bit worse than the previous setting. However, the PGRN, which is a combined method, still perform robust. While the pure machine learning model RNN seems fail to give an accurate prediction under this setting. So for other more readings on this generalized loss function design, uh, audience can refer to these different papers listed here. Well, this is going to be the end of this part. And in the next, my colleague Xiaowei is going to introduce other different methods in utilizing domain knowledge to help deal with a small data issue. Thanks for your attention.
Hello, everyone. This is Xiaowei Jia from the University of Minnesota, and I'm going to join the University of Pittsburgh as a faculty member starting from fall 2020. And today I would like to cover the use of domain knowledge for model initialization and model design. So now that Zhengjie has covered that it's possible to use domain knowledge to guide our design of loss functions. But in practice, there are many more general and more complex relationships or domain knowledge that cannot be directly expressed as part of the loss function or as a regularizer. And also sometimes it's just because these relationships are not differentiable, even after we do some approximations. So that's why we are thinking whether it's possible for us to directly transfer knowledge from these domain knowledge-based models itself, because these domain knowledge or DK-based simulator, they usually contain many different types of domain knowledge, and these domain experts may spend like 20, 30 years in building such kind of DK-based models. So they contain very rich information. So one thing is like we can use this, or we can treat this DK-based simulator as a black box. And then we can run this DK-based simulator to generate simulation data. And then we can use such simulation data to pre-train our machine learning models. And basically, by doing this pre-training, we are using machine learning model to mimic the behaviors of this DK-based simulator. And the idea is that we know, like these days, these machine learning models, deep learning models, they have very complex structures. They usually require a large amount of training data to tune those model parameters. But we know like these DK-based simulators, running this DK-based simulator doesn't require any true observation data or training data. So that means we can generate large amount of simulation data. And if we can pre-train this complex machine learning model using large amount of simulation data, then it's very likely that this machine learning model can already get much closer to its target solution. Then it only requires very few amount of true observation data to fine-tune itself to get to this target solution. And we show this process of pre-training and fine-tuning using these two pictures at the bottom. So basically, we can see that during the pre-training phase, we are actually using our machine learning model as an emulator for DK-based model. But remember, like DK-based models, they usually use a lot of approximations. So that means they usually have certain inherent model bias. So there can be a gap between our simulations and the true underlying patterns. But still, because these DK-based models is usually being built using many general domain knowledge or physical relationships, so it's still able to some extent, these DK-based models can capture these kind of spatial and temporal relationships that are used to build these kind of DK-based models. So once the pre-trained model can correctly capture such kind of spatial or temporal relationships, then what it needs is just very few true observation data points along these underlying true patterns to close such gap. And that's how fine-tuning works. And here we've shown some results for the same example of modeling lake water temperature. So these experiments is conducted in Lake Mendota in Wisconsin. And Lake Mendota is actually the most widely studied lake in US. And here we implemented 3 different types of methods. The first one, general lake model. And that this model is purely physics-based model, or it's purely based on domain knowledge. And it's also the state of the art for modeling lake water temperature, and it's currently used by USGS. And the second one is a pure black box machine learning model, recurrent neural network model. And here we use the long short-term memory cell within this recurrent neural network structure. And the third one is our proposed method, basically is the same recurrent neural network model, but first get pre-trained using the simulation data generated by this general lake model, and then get fine-tuned using our true observation or training data. And all of our training and testing data are randomly selected from a 9-year period from 2009 to 2017. And as we mentioned, like in the pre-training phase, we can use large amount of simulation data. So in this case, we do the pre-training using the simulation data from the past 30 years. And in this figure, we show the performance. So here, the x-axis is the number of training samples, and y-axis is the prediction error or the prediction RMSE. But it's in the reverse order. So basically, we can see the 1 is on top and 4 is at the bottom. So basically, the higher, the better. And if we see these curves, if we just compare this RNN and the GRM, the domain knowledge-based models, we can see that when we have sufficient training data, then this black box machine learning models performs much better than this DK-based model. And the reason is that this DK-based model, they usually use a lot of approximations because there are many physical processes that are still not fully understood by these domain scientists. So they have to use certain approximations to represent these physical processes. And by using these approximations, they introduce some additional model bias so that even if they have access to large amount of training data, they can still not fix this kind of model bias. But on the other hand, if we only use very few amount of training data, then we can see this machine learning model performs much worse. And the reason is that these machine learning models can easily overfit the training data. But this GRM or the DK-based model, the performance is relatively stable, and that's because it mostly rely on this kind of general physical relationship. And by combining these two types of models, or by doing this per training, we got this top curve. And we can see this top curve, our proposed method actually has much better performance than either GRM or this RNN model. And especially like we can see, even if we use just 2 days profile for training, we can still get better performance than the DK-based model. And assume like if we have infinite number of training samples, then we can imagine this black box machine learning model, RNN, and this pre-trained and fine-tuned model, they should have quite similar performance because the data size is already sufficiently large for this black box machine learning model to capture all this complex relationship by itself. So in this case, the pre-training is not very useful. And here we show an example of these water temperature predictions and see how this pre-training and fine-tuning can help change these predictions. So basically, these predictions are the water temperatures in the middle layer of Lake Mendota. And these blue dots here are the true observations for water temperatures. And this green line is the simulation data produced by this GRM or the DK-based model. And if we just pre-train a machine learning model, an RNN model using this simulation data, then we get this black line. So we can see the black line can almost capture all the dynamic patterns of these simulation data. But still, this black line has a large gap with our true observation data. Then if we only fine-tune this pre-trained model, this black line, using just 2% of true observation data, then we can get this red line. We can see this now this red line has a much better matching with the true observation data. So this really shows that even if our simulation data is not perfect, it has large bias with the true observations. But still, by doing the pre-training using such simulation data, the pre-trained model have a higher chance at learning these kind of general seasonal patterns over time. And once we can get these seasonal patterns to be correct, then from there, we only need very few amount of true observation data to close this gap, to get this red line. And another major concern about using this pre-training strategy is that sometimes we may not have access to a set of perfect parameters within this DK-based model to generate good simulation data. So for example, in this lake modeling case, one key parameter in this GRM, in this DK-based model is the geometry of these lake systems. So for example, this Lake Mendota, this is a true geometry of Lake Mendota. But if we don't have this information, we have to rely on some default parameters. So the first three pictures, martini, cone, and barrel, there are some default parameters for lake geometry. So here in this slides, we just want to show like whether these pre-training are still going to be useful if we just use imperfect simulation data generated by using these default parameters. So basically here we can see that if we do the pre-training using this simulation data generated by these default parameters and without doing any fine-tuning, so we use 0% of data for fine-tuning. That means we just pre-train the model. And we can see the performance can get much worse. The prediction RMSE can get much higher, especially for barrel shape and martini shape. And that's because we can easily see that this martini shape and the barrel shape, they are far away from the true geometry of Lake Mandela. The cone shape is relatively similar. So that's why we can see the cone shape, the performance is very close to the performance using the true geometry. But even if this performance is getting much worse for the pre-trained model, but still we observe that as long as we feed in a small amount of true observation data for fine-tuning, like 2% or 20%, then we can see this machine learning model can quickly recover to get reasonable performance. So this shows that even if these simulation data are not perfect, are using a wrong set of parameters, but still by doing this pre-training, these machine learning models still have a higher chance to learn some general relationships that can be helpful for these prediction tasks. Another good example is for traffic signal control. So basically here we are trying to determine the optimal strategy for control these traffic signals. And this problem actually can be naturally formulated as a sequential decision-making problem using reinforcement learning, where we have the input states, which consists of the current traffic volume from each lane, and also the current traffic signals. And we are trying to determine what should be the traffic signals that we should give at the next time interval. And the reward is based on the total queue length for all the lanes. So basically, the shorter the queue length, the higher the reward. But one big concern about reinforcement learning is that usually we need a good or reasonable initial model to start with. And to get such initial model, these authors in this paper, they propose this strategy that they can first run a decay-based model called SOTL. So this is basically a simulation-based traffic model. And they can run this model to generate a set of simulation data samples, and each data sample consists of these 4 elements: the current state, the next state, and the actions being taken, and the reward received by taking this action. Okay, so once we collected large amount of these simulation data samples, we can use them to train or pre-train this reinforcement learning model so that we can get a good initialized point. And then from there, we can fine-tune this reinforcement learning model using some true observations by doing this actor and critic algorithm. So this method have shown to be able to greatly improve the performance on this traffic signal control. So now that we have covered that it's possible to use domain knowledge to guide or to use such kind of domain knowledge in different types of learning strategies, like in the design of loss functions or in doing this initialization of machine learning models. But in the following slides, we're going to show that it's also possible to use such kind of domain knowledge to even modify the internal structure of these machine learning models. So we start with encoding intermediate domain variables. So basically, we see these days, these neural network models or deep learning models, they have found a lot of success in different applications. And the power of these types of models mainly comes from their ability to extract these hidden variables or hidden units in the middle layer. So these hidden variables are basically some abstract representation that are, we hope that these hidden representation are more relevant to our prediction tasks. But in practice, if we only have access to limited number of training data, then these learned hidden representations can be less meaningful. So something we think we propose here is that we can enforce to learn some domain variables in the middle layer, so that we can force these machine learning models to learn patterns or learn these representations that are consistent with our known domain knowledge, so that the model can become more generalizable. So here we use the same example of modeling lake water temperature. So basically remember, like in this example, we are trying to maintain a lake energy budget, which is the lake thermal energy. And this lake thermal energy is affected by the difference between incoming and outgoing energy fluxes. So if we have more incoming energy than outgoing energy, then this lake energy budgets should increase, right? So one approach to model this phenomenon is that we can construct a new architecture to force the model to memorize such kind of energy transfer process. And specifically, we start with building the standard recurrent neural network. So basically here we show in these black colored arrows, these black colored arrows represent the standard recurrent neural network framework, where we also use the RSTM cell as a recurrent cell structure. But on top of that, we also introduce another recurrent process, which is shown in this blue color. So in this blue color, this energy flow, we also introduce another set of physical states and physical variables. So here, basically, these physical states are very similar to the RSTM states used in the standard recurrent neural network model. But the difference is that these physical states, they have some real-world interpretation. So that means they correspond to some real physical variables. And in our example, in this lake temperature modeling example, these physical states represent the lake thermal energy at every time step. And the physical states at each time step can be calculated by combining the physical state at previous time step and also some intermediate physical variables. And here, these intermediate physical variables basically include different types of energy fluxes like solar radiation, basically these incoming and outgoing energy fluxes and so on. So remember, like in our previous, when we previously talked about this example, we mentioned like lake thermal energy, the change of lake thermal energy is dependent on the difference between incoming and outgoing energy fluxes. And by introducing or by using this additional energy flow, we are expressing the same kind of relationship. The physical state is dependent on the previous physical state and also this additional net gain of energy fluxes. So by using this energy flow, basically we're trying to force this machine learning or this recurrent neural network model to capture this kind of energy transfer process, which really drives the change of temperature in these lake systems. So that's how we can encode some intermediate physical variables in a machine learning architecture. And we can further extend this framework to model some even more complex scenarios. And here, this example is about modeling water temperature in river networks. The river network is more complex because we have to consider the interactions between different river segments. So basically, the river networks consist of multiple river segments, and these river segments can be connected with each other. So for example, here we show a very small network with just 3 river segments, A, B, and I. But there's a lot of frequent interactions between them. For example, the water can get evected from upstream A and B to the downstream segment I. So this water, when it merges from upstream segment A and B to the downstream segment I, this water can directly impact the change of water temperature for this downstream segment I. So actually, this kind of relationship can be very naturally modeled by using a graph convolutional neural network, because we know that this graph convolutional neural network can automatically figure out such kind of influence between different nodes in a graph. So if we represent each river segment as a node in this graph, then we can build an edge from A to I and from B to I so that we can propagate influence from the upstream segments to the downstream segment I. So basically here we see that when we calculate this RSTM cell state for the downstream segment I, we also incorporate the hidden states from A and B. So basically we call them HA and HB. So HA and HB are the hidden units extracted from upstream segments. And then after some transformation, we convert them into QA and QB. And then these hidden variables QA and QB are going to be passed to the RSTM cell to model water temperature for the downstream segment I. But in the standard graph convolutional neural network, all these hidden variables are learned automatically. So they may be just some abstract representation. And these kind of hidden variables can become less meaningful if we just train this model directly using limited amount of training data, as we just mentioned. So one way is that we want to enforce some domain knowledge so that we can guide the learning of these hidden variables, so make them more meaningful. And according to the energy conservation law, we know that the change of temperature is dependent on the difference between incoming and outgoing energy fluxes, and also is dependent on additional net heat advected from the upstream segments. So basically this term HADV measures the impact from upstream segment A and B to the downstream segment I. So this should be the information that's going to be passed or propagated in this graph network. So, and also according to the physical formula, we know that this HADV term can be calculated as a function of a set of intermediate physical variables. So these intermediate physical variables are basically some physical properties of this upstream segment A and B. So they include like stream flow, like the temperature of these segments. And actually it's very intuitive because we can imagine like when the water merge from this A and B to the downstream segment I, then this stream flow, like the velocity of these rivers and also its water temperature can directly impact the water temperature change for the downstream segment I. So that's why we have to estimate these intermediate physical variables. So, so what we do is we represent these intermediate physical variables using the symbol SA and SB in these dashed circles. And then we define new loss function such that we can extract. So by minimizing this loss function, we are trying to ensure that we can extract this set of intermediate physical variables SA and SB from these hidden units QA and QB. So if we can extract these variables SA and SB from QA and QB, then it means this QA and QB, these hidden units, indeed contain sufficient information to represent these intermediate physical variables. Then once QA and QB are passed to this LSTM cell for the downstream segment, then this LSTM structure can gather sufficient information to represent or to estimate this term HADV. So this is basically the impact from upstream to downstream segments that we're going to estimate. So basically, this method have shown to be able to greatly improve the prediction performance for water temperature and also make the model more generalizable because we enforce some very general physical relationship here. And also here we talk about some other examples about encoding other types of more general domain-specific knowledge in these two applications. The first example is about predicting human ages from neural images. And this work is published in 2018 by Sternfels. So basically what they do is they introduce additional neural network layer at the beginning to segment this brain volume into different regions. And this segmentation is based on our domain knowledge about neural images. And then this information from different regions can be treated as different channels and get fed into the following convolutional layers. And this method have shown to be able to improve this prediction performance. And the reason is that by using this first layer, this segmentation layer, we can extract some more representative or more discriminative features. And also those features should be more relevant to this prediction tasks because these segmentation tasks is based on certain domain knowledge in this neural image domain. And the second example is about a data generation. Basically, we are trying to simulate the super resolution fluid flow. Okay, so this method is based on, again, the generative adversarial network. So remember, like in standard GAN-based model, we have a generator and also we have a discriminator, and they're combating with each other. So here they extend the standard GAN model to by introducing two different discriminators. And one discriminator is used to preserve such kind of spatial coherence of the simulated data. And the other one is based on the, is used to guarantee this temporal coherence. And the design of both of the two discriminators are based on certain aspects of domain knowledge in this, in CFD. So the idea of all these approaches that we have seen that using domain knowledge in designing machine learning architecture is that by using such kind of decay-informed model architectures, actually we can greatly reduce the search space for model parameters. So we can regularize certain layers or certain hidden units. And so in this way, we can reduce the search space for model parameters. And that's why we can train this model using maybe much fewer number of training samples. And also by enforcing this kind of domain knowledge into the model architecture, actually these machine learning models have higher chance at learning patterns and relationships that are consistent with our known prior domain knowledge. So in this way, because this domain knowledge can hold in different scenarios, so our machine learning models can also become more generalizable in different scenarios. And here we talk about a more general problem of search for the optimal neural network architectures. And we have the same objective here, which is to learn a predictive function f from input features x to the output target variables y. But here the hypothesis space consists of not only the network parameters, but also the architectural parameters. So basically we have to determine, like, for example, what kind of connections should we use to connect each pair of hidden units or from hidden units to the output units. For example, whether we should use the fully connected layers or whether we should use the skip connection layers, and so on. But here, what these authors proposed in this paper published in 2019 is that we can also include some physical operations as additional options for defining these connections between hidden units to the output units. And for example, like, consider the problem of modeling the trajectory of a ball after we tossing it for some time. So according to this free-falling equations, we can have a roughly guess of the position of this ball after we toss it for a certain amount of time. And by including such options in this neural architecture search problem, actually it provides us with more flexibility, because we can imagine, like, if we don't have sufficient training data, then we may prefer to use such kind of physical operations, because we can notice that these kind of relationship defined by these physical operations, they're relatively fixed, so they don't require much tuning. So this relationship is already well defined. So that's why they don't require much training data to tune those parameters in this relationship. But on the other hand, if we already have sufficient training data, then we may prefer to use machine learning or purely data-driven based connections. And the reason is that by using these kind of purely data-driven based connections, we may have higher chance to do a better or do a more accurate predictions. And that's because we can see that these equations, like free-falling equations and some other physical operations, they're usually based on many assumptions. And those assumptions may not always hold in real practice. So that's why the author proposed this kind of hybrid framework where we can intelligently choose, like, whether we want to use this kind of physical operation or this purely data-driven approach to define this neural network architecture. And here we also list some more literatures to incorporate domain knowledge into machine learning models. So previously, we have shown that it's possible to use domain knowledge in designing the architecture for neural network architectures, neural network model, like the hidden layers, like the hidden layers, and also like the entire structure, like the additional layer or the hidden units. But also here, in some works, they have talked about it's also possible to use such kind of domain knowledge in guiding the design of the kernel for Gaussian processes. And also in many scientific domains, they have commonly exist such kind of monotonic relationships. For example, we know the relationship between water density and the water depth. So for example, the denser water in the lake system should always stay in the lower part of the water column. So there are also some previous works that have shown that it's possible to preserve such kind of monotonicity relationship in the machine learning models. And by preserving such kind of relationship, we can also improve our prediction performance. And also by using domain knowledge, we can also better tell, like, which groups of tasks are more relevant with each other. So these can help us select auxiliary tasks in doing multitask learning, because only by select the relevant groups of tasks, then we can learn knowledge from one task and then use such learned knowledge to guide the learning in the other task. And to conclude this tutorial, so we have shown that there are so many different approaches for learning with small amount of data, and we believe such kind of research actually can be very promising, very useful in many cases, because we can easily find many use cases in our daily life where this data collection can be very challenging, or the manual labeling can be very expensive or can be very time consuming. Like for example, in our lake modeling case, collecting these samples, the label samples from one single date may cost like $2,000. So it's a lot of money. And also it requires like domain experts to do this labeling. So we cannot find some random people to do this labeling. So that's also a lot of substantial human effort involved. And in particular, our approaches that covered in this tutorial can mainly fall into these two categories. One is to transfer knowledge from auxiliary tasks, and the other one is to transfer knowledge from domain experts. So basically, the idea is quite simple. Like if we don't have sufficient information from our training data, then we have to take it from somewhere else, either from auxiliary relevant tasks, or we should take it from some accumulated knowledge in specific domains. And specifically for the first topic, transfer knowledge from auxiliary tasks, we cover 3 different methods: transfer learning, multitask learning, and also meta learning. And in meta learning, we also covered like 2 major challenges. One is the task heterogeneity, and the other is meta overfitting. And then for the second topic, transfer knowledge from domain experts, we have shown that it's possible to use such kind of domain knowledge to guide the design of our loss functions, and also for doing the model initialization. And finally, we have also shown that it's possible to use these domain knowledge to guide the design of model architectures. So that's pretty much about everything about this, this tutorial, and really thanks for listening. So please feel free to contact us if you have any questions. Thank you.